Okay, so where we left off last time was talking about the various layers of Android. I talked about the operating system and protocol layers, the hardware layer. We talked about the different middleware infrastructure layers. We talked about some of the higher layer middleware, such as the application framework layer. We talked very briefly about the applications themselves, which are really what matters when it all comes down to it from a user point of view. And what I thought I'd do now is kind of go into a little bit more explanation of what are layered architectures. Now that you've seen some examples of how they apply in Android, we'll talk more broadly about the concept in general. And this will give us a chance to sort of think about some interesting patterns that get applied in these types of environments. So we'll also talk about the layer pattern, the layered architecture pattern, and you'll get a chance to see how Android applies that. Another thing we'll talk about is why Android uses layering. It's not just enough to know that it does use layering, it's also useful to understand the rationale, what's the purpose behind doing this. And this will also give us a chance to talk more broadly about the concept of layering in systems in general, and you'll see why it's a very common way of designing complex software. So obviously layering is applied in lots of domains, not all of them computing, but we care about them primarily in the computing domain. A really good example of layering, which you've hopefully seen or will see when you take the networking course here at Vanderbilt, or a networking course, is the concept of layered protocol stacks. So there's the classic so-called OSI reference model layered architecture, which has 7 layers, as you can see here. There's also the internet protocol stack, which has 4 layers, plus other stuff that layers on top of that in practice. And basically what these protocol stacks are doing is they're specifying how communication should take place end-to-end in a network system in order to be able to transmit data reliably from sender to receiver in a way that can be properly marshaled and demarshalled and packetized and unpacketized, addressed, transmitted, routed, received, all those good things. And so that's probably the most common example of layering that you're likely to run across if you study networked systems. So in the networked environment, the lower layers, the link layer, the physical layer, handle the interactions with the hardware, and these would include common protocols like, say, GSM, which is a standard that's used very widely in Europe. It's used a little bit over here, increasingly over here. Digital subscriber line, DSL, Ethernet, very common link layer protocol that you'll find all over the place. The middle layers in the OSI model handle exchanging packets between end systems and intermediate router nodes and being able to get the data sent from one end to another, either unreliably using something like the user datagram protocol or UDP, or reliably using something like the transmission control protocol or TCP. And it's beyond the scope of this course to talk about that, but you've undoubtedly at least heard of these things. And the internet is really largely based on TCP and IP. That's the underlying infrastructure for communication. The upper layer parts of the OSI model, which are somewhat strangely absent in the internet protocol model, are what are called the session layer and the presentation layer. And these are really intended to simplify interactions with applications. So there's various protocols that handle exchanging data in binary format between hardware systems with different ways of arranging the bytes and the bits. There's ways of being able to encode data so that you can process it in a more text-oriented way with things like JSON or XML, and so on and so forth. So these are some examples of sort of upper layer stuff. And then, of course, the application layer is where all the interesting applications live. And in the common networking infrastructure, here are some examples, relatively simple examples of applications, things like FTP, the file transfer protocol, Telnet, the simple mail transfer protocol, the SNMP, which is a network management protocol, simple network management protocol, simple mail transfer protocol, and so on. So those are examples of other protocols that get used, or applications that typically run. And then everything else layers on top of those things too. So that's one example of layering. Another example of layering that you'll run across all the time if you program networked and distributed systems, such as Android, would be what's called communication middleware. And this is very commonly found in multi-tier enterprise IT systems. It would be found in one way or another in certain cyber-physical systems or distributed real-time embedded systems and so on. And this is basically, everything we just talked about on the previous slide, all these layers, in this worldview lurk underneath in here. So the operating systems and protocols portion, the protocols part is really where all of these layers reside. And then there's a bunch more layers that live on top of that. And the purpose of the middleware layers is to basically shield application developers from all the details of what's going on in the underlying network. And in fact, another way to look at this is, if you take a look here, you'll see that we have this sort of application layer, presentation layer, session layer. These layers that I said are not really present in the Internet Protocol stack, and they're somewhat underspecified in the OSI model. These layers really are what expand up to all of this stuff in the communications middleware stack. And so some examples would be things like host infrastructure middleware, which essentially provides an encapsulation of the hardware and operating system APIs so that programs don't have to be dependent on the operating system interfaces, but instead can write in a more portable way. So obviously, Linux and Windows are examples of operating system APIs. And host infrastructure middleware would include things like the Java virtual machine, which, among other things, encapsulates the underlying operating system, so you can try to get this write once, run anywhere style of portability. There's other stuff like ACE. I developed a framework that helps to encapsulate operating system diversity in C++. So those are examples of layers of middleware. By and large, these days, if you program in modern environments like Java, you don't really think too much about this stuff because it's provided for you with things like the Java class libraries and the JVM. They hide all these layers from you. Another piece of the stack here is something that's called distribution middleware. And that basically shields the applications from the details of network programming. So if you write code that has to run across a network, you have to deal with all kinds of things related to connection management, data transfer, multi-threading, dealing with these issues of endianness, trying to deal with differences in hardware, just demultiplexing. There's a whole bunch of things that you have to deal with. And these services, these middleware services, hide all that from you. So instead of having to program in the lower way, which was the old way of doing things, instead you can use middleware frameworks that let you make method calls on objects or send messages at a high level, and they manage all the details of how that stuff is going to be sent down to the lower layer parts of the system. So examples of this would be things like the data distribution service, Corba, Spring, MQTT, web services. These are all examples of these higher layer services. And then the top of this stack are the so-called domain-specific middleware services. And they basically encapsulate large chunks of domains with other components and services and microservices and APIs to allow people to really abstract away from the details of writing certain kinds of apps. So for example, if you're writing apps that are going to be avionics oriented, there's something called the Future Airborne Combat Environment, Future Airborne Capability Environment, FACE. And they define a whole bunch of APIs that are specific for people writing avionics systems. If you're building an electronic funds transfer system, you probably don't care about most of what's in FACE. But if you're building an avionics system, you really do care about that. There's also other domain-specific services in the medical domain, in the Internet of Things, or the industrial internet, and so on. So these are kinds of services that you would find if you're programming in a particular space or a particular domain. Not necessarily as widely standardized, but you'll find that if you work for a company where you have to do insurance or electronic funds trading or missile defense or whatever. Yes, Kelsey. Typically, these would be frameworks provided through language bindings. So just to give you an example, FACE is defined in such a way where there could be a Java implementation of these APIs. There could be a C++ implementation of these APIs. There could be a C implementation of these APIs. And so the language that you use to access these domain-specific middleware services, relatively agnostic, as long as you have a binding. And oftentimes those bindings are described with things like WSDL, which is the web services definition language, or the interface definition language, IDL, or the Android interface definition language, AIDL. People will come up with higher level ways of defining interfaces, which include methods and their parameters. And then they have mappings from those interface definition languages into your favorite programming language, Java, C++, C, Ada, Python, whatever. And the reason for doing that is just so that you don't have to become wedded to one particular language. Because people typically, oftentimes in these environments, want to write their client-side code in a different language, even in a different platform, than their server-side code. You might want to write your client-side code in JavaScript, but you might want your server-side code to be written in Java or C or C++ or whatnot. And so using a more language-agnostic or language-independent abstraction allows you to do that, and then you generate the code, or then a tool generates the code to map into whatever language you use. But yeah, that's a great question. So, what we teach you at Vanderbilt is typically, more the lower level stuff. Now, if you take the web development class, which some of you probably have or will do, they'll teach you a bunch of web services related stuff, and that would kind of be in this layer. We typically don't teach a lot of domain-specific stuff here because we're really trying to give people general purpose skills, but you might learn some domain-specific stuff. For example, if you were to go work as an intern for the medical center, they might teach you some tools there that would be very medical-centric specific. Or if you go out and do an internship with a company where they're doing a lot of web development, you're going to learn domain-specific tools, probably JavaScript-based stacks like React Native or Angular or Node.js or something like that. And those are more domain-specific things for different kinds of application environments. Okay, so the point of this is just to say that the applications may deal with one or more of these layers. And in modern practice, sometimes you'll write applications that work directly on top of the operating system. Mercifully, that isn't happening as much anymore as it used to, but it still happens once in a while. More likely, you'll access things through one or more of these layers, right? So if you're writing Java apps, you might, if you're writing sort of to the native, or the lower layer parts of Java, the Java class libraries, that's kind of host infrastructure middleware. If you start doing things with stuff like enterprise Java Beans or Spring, then you're moving up more into the common middleware services and distribution middleware portions where the distribution aspects are hidden from you by the underlying capabilities provided by the frameworks. So all of that is really just to provide you with some concrete examples of the more generic point here, which is the concept of layering. And so to explain that, we'll talk about a pattern, which is known as the layers pattern, or layering pattern. I guess it's called the layers architectural pattern. And this is a good example of something called an architecture pattern or architectural pattern. A lot of the patterns that you have been exposed to up to this point are in a class, for example, like the 251 course, have largely focused on design patterns, which deal with relatively small numbers of roles and responsibilities, a couple of classes, right? If you think about the bridge pattern or the observer pattern or the strategy pattern, there's a couple of classes that are used. And it doesn't really, those patterns, those design patterns, don't really look comprehensively at an architecture. It's really just a microarchitecture, a small piece, a postage stamp-sized piece of something. So architectural patterns, as the name implies, are looking more architecturally at what you're trying to do. So basically, if you take a look at what an architectural pattern is, it has a bunch of stuff. It has a way of organizing. It's a structural organization schema. Think of schema kind of as a blueprint, perhaps, or a boilerplate template or something. That's probably too narrowly focused, but think of it like a blueprint for software systems that provide a set of predefined subsystems, which, as we'll see, will be often layered, specify the responsibilities of each of the subsystems, or the layers, and then include rules and guidelines for organizing the relationships between these various roles. So it's all about, how do you take a big problem space and chunk it up into smaller pieces, define the interfaces, and then explain how you're going to communicate between the different subsystems. So that's what an architecture pattern is in general. Layers is an architectural pattern described in various places. It was first, it's been around forever, but it's been documented as a pattern initially in this book, which is the Pattern-Oriented Software Architecture Volume 1 book. And then it also appeared some other places, including the Volume 4 of the Pattern-Oriented Software Architecture series, which I co-authored with my colleagues. And in this case, we show some examples. In fact, one of the examples we use of layers in this particular book, Volume 4, is that communication middleware example we just looked at. So we show how that applies there. Here's basically how layering works. The cool part about this is, as we go through this, you'll see this is exactly what Android's doing. But really, Android is just an embodiment of these more profound concepts of how to break a complex piece of software with millions of lines of codes and probably tens or hundreds of thousands of methods and thousands of classes and so on into something that can be understood in a more modular and incremental way. So the layers pattern works as follows. You end up with layers. As you can see here, we have some layers. And you have, at each layer, you have a bunch of functions that are providing a service or a group of subtasks. And as you can see here, you have the interface, which is really the sort of the API. You can think of these as functions or methods or whatnot. And then, of course, you have the implementation of that interface. Naturally, the people who use a given layer, like layer C, they will only interact with the implementation through the interface. And under the hood, you'll have different implementation details that will realize those implementations. That's just simple abstraction, right? So what's interesting about this is, of course, we have abstraction, which is what I'm showing you here. But then we're going to organize those abstractions in terms of levels of abstraction, or the layers themselves. So each layer has a set of capabilities, and then the layers are going to be kind of stacked up on top of each other. And then they can communicate, typically, sort of in a bucket brigade-like manner, although we'll see there's other ways to implement it. So why is this a win, right? And first of all, hopefully when you look at this diagram, and then you think about the Android architecture I showed you that we've talked about for a couple days, it should look very similar, right? Layering helps to simplify software development and evolution. And the reason it does that is it moves away from what are called big balls of mud, or spaghetti architectures like the one that I'm showing you here. And instead it replaces them with a much more modular way of organizing the software that can be extended and contracted more easily. So if you take a look, you can see, if somebody gives you this piece of software to maintain where it's really hard, you just have to sort of memorize hundreds of thousands of classes and methods, your mind will explode and you'll have a very hard time explaining what's going on. In contrast, if somebody chunks it up into these levels of abstraction, it's easier to follow, and we'll see why in a second, because you only have to focus on a small number of things at any given layer. Now, it would be nice if you could just layer everything and be done, but of course, it's more complicated than that. And one reason it's more complicated is if you're not careful and you don't design your system with performance in mind, you can end up with a lot of extra overhead to move information back and forth between the layers. So that's the kind of the downside with layered systems. If you're not careful, is you can have a lot of overhead. And there's ways of getting around this we'll talk about shortly. In fact, one of the things you'll see a lot of, in fact, this is exactly what's used in Java 8 streams, is the concept of integrated layer processing. So remember when we talked about Java 8 streams, and we talked about how when you have a stream pipeline with stream, blah, 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 dot filter, blah, 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 dot map, blah, 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 dot flat map, blah, 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 dot filter, blah, 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 dot collect, or whatever, right? Some pipeline of things. And I explained a number of times how the actual flow of data through those stages in the stream pipeline doesn't go from left to right and then down, like a typewriter. Instead, what happens is, the way streams work is it pulls the data from the source of the data through a bunch of functions, bunch of behaviors, and then eventually collects them all together. And that's what's called integrated layer processing. So we don't do all the work at one layer and then pass the results to the next layer, unless it's a stateful operation, stateful intermediate operation. But instead, we typically pull them through. So that's an example of an optimization you can apply to a layered system to make it more effective and to work better. The main thing you want to do, and this is really important when you design layered systems, is try to minimize key sources of overhead. And these would include things like context switching, synchronization, data copying overhead, and so on, because those are the things that will slow you down if you're not careful. And it's only because of the fact that hardware keeps getting faster, that and networks keep getting faster, that we can layer our systems as much as we do these days. Back in the day, back when people, say, were first developing mobile device software for those old flip phones and the candy phones that you used to have, the candy bar phones that used to be very popular, those things were not written in a layered way, or a very minor layered way, because it was just too much overhead to move between layers. Nowadays, we've got a lot more memory, we have a lot more processors, the batteries are better, the networks are faster, and so on, so we can afford layering, but you still have to be thoughtful about it and not do stupid things. Okay, so now that we've talked about the concept of the layers pattern, let's talk about how Android applies this particular pattern. So again, you should be able to see, literally, visually, when we take a look at a diagram like this, which is what the pattern describes, and then we go ahead and look at this, which is the Android architecture diagram. Surprise, surprise, it really is about the same thing. It's about layering. As we've talked about before, the Linux kernel layer is what controls the hardware and manages access, shared access to system resources. We've got these multiple layers of middleware. We have the middleware infrastructure layers. We have the application framework layer, lots of frameworks running around inside it. And these basically raise the level of abstraction to program apps, so the apps don't have to know anything about the low-level OS kernel APIs, but instead they can work with more familiar, more convenient abstractions like objects and services and so on. So hopefully that makes sense to you guys. You would not want to have to write Android apps directly atop the Linux kernel. Your mind would explode. Yes, Max? So good examples of some of the earlier ways of designing software. There was a Motorola, I think it was the Motorola operating system. I'm using the word loosely. I think it was called something like P2K. I forget why it was called P2K. But basically, it was just a bunch of functions. It was kind of like programming to the Linux operating system APIs. And so your, quote, applications had to do all the things that today would be handled by these layers of middleware. So, if you wanted to be able to do anything having to do with, first of all, the applications were ridiculously simple. It was like, make a phone call, look somebody up in an address book. That was about it, right? If you look back at the old operating systems and the old features available on the early phones, they just didn't do anything. Or the applications they had were very, very meager. In fact, I'll never forget one time I interviewed at Motorola many years ago, many years ago, and while they actually still had some development work up in Illinois, and one of the guys I was talking to said when Motorola had first come out with a mobile phone, there was reluctance on the part of some people on the design team to have a contacts app on the phone, and the rationale was, that's not how you use your phone in your house. You have a separate white pages or yellow pages, which you guys may not even remember what those were, but back in the day, people would drop off, yellow pages and white pages, which are big, thick, bound stacks of paper on your driveway, like once or twice a year. And that's how you would learn how to make phone calls. None of that stuff was actually on the phone. So the operating systems were so simple that they just didn't have anything. They didn't have any applications. They were just phones and maybe an address book, maybe. Even that was pushing it in some cases. So back in those days, a mobile device was a phone with a couple of tiny computing functions on it. Nowadays, a mobile device is a computer that happens to have a radio on it, right? So that's been the real transition. And iOS and Android are really the things that have accelerated this perspective. There were intermediate technologies. For example, there was something called Symbian, which was a development framework or environment, I guess, for Nokia and Ericsson and a few other phone manufacturers that had some stuff in it, but it was very, very crufty and very limited. In fact, the thing that did Symbian in, the reason why the Symbian-based phones have almost entirely disappeared, is that they really couldn't add touchscreen support to Symbian for some reason. They could only, the most they could ever do were either, keypad stuff, physical keypad, or, like pointing device. This takes you back to the bad old days where you used to have a little stylus in your phone. And God help you if you ever lost your stylus because you couldn't do anything, right? I guess you could make a phone call, but you couldn't do much of anything else. So the point of all that stuff was that there were early attempts at trying to build what are called feature phones that had some apps on them, but they were extremely limited, and that's because the people in those days had a hardware-centric view as opposed to a software-centric view, and they didn't have very effectively layered solutions. Okay, so middleware gives you all these capabilities that otherwise just didn't exist, and so there were only a few meager apps because you had to reinvent all this kind of stuff on a one-off solution based on top of the lower-level kernels. And then the application layer is what really provides the packaged functionality that we use. That's what people really care about, right? You want to have access to the 2 million apps or whatever that are available on the Play Store or iTunes and so on. So why do we use layering in complex systems like Android, right? So here's a more abstracted view of Android. This view here that we see. That's the official, or one of the official views of Android layers. Here's a more abstracted view that really is focusing on the layers more than the details of what's in the layers. So there's a couple of reasons. One of which is to enhance systematic software reuse. So by using a layered model, the Android development team could hit the ground running much more rapidly because they could do things like leverage the existing Linux kernel with plenty of modifications, of course, but they didn't have to start by writing a kernel from scratch. What a nightmare, right? That would be really hard. It takes a long time. That's why they decided to use a variant of the Linux kernel. And then there's also other things that are taken off the shelf, right? So the class library APIs, the so-called declaring code of the Java class libraries, those were things that were systematically reused. Lots of the implementation details of the dozens of native libraries like WebKit, SSL, SQLite, lots of things that come off the shelf, type libraries, OpenGL, graphics libraries, and so on. All of those things are taken off the shelf. So that's also another example of systematic software reuse. You don't have to rewrite all those things from scratch. You can just leverage them and tweak them as you need to. There were, of course, some things that they did add, but even those things are carefully partitioned into different levels of abstraction, making it easier to maintain, easier to evolve, and so on. Another motivation for using layering, another example of systematic software use is the libc library. And so libc is essentially the standard C library that's used to access the Unix kernel or Linux kernel capabilities. So libc is a common API, and anybody who knows how to do Unix systems programming understands libc. So it's got methods like open, close, read, write, socket API calls, thread API calls, and so on. We already talked about how we can use the runtime system to abstract away from the multi-core hardware. Another reason for layering, another reason why Android uses layering, is to enable plug-and-play replacement of certain layer implementations. So, at least in theory, the use of things like the hardware abstraction layer allows hardware to be kind of plugged and played by the OEMs, by the phone manufacturers, in ways where they can provide a relatively stable API to developers on their platform, people who are writing variants of Android for a particular hardware suite with particular processors and GPUs and DSPs and sensors and transceivers and all the good stuff we talked about before. And the hardware can be changed without really breaking much of things that rely on it. So it's much more plug-and playable. And another reason for doing this, of course, is you want to be able to make sure that if you make a change to a layer implementation, ideally it shouldn't break anything else, right? You're kind of confining the implementation details at a given layer to just the internals of that layer, and anything that lives on top of it shouldn't change if the implementation details change. Sometimes it's easier said than done, but it's not too much of a stretch. In fact, if you think about it, an operating system API like libc provides you makes it possible to write apps that, at least in theory, should run on many different hardware platforms, many different implementations of that operating system. And as long as all the operating system implementers have the API specified properly, and then have the implementation of that API be faithful to the semantics that the API is trying to provide, then you can change the hardware, you can actually change operating systems, and all the other stuff should more or less work. Now again, sometimes it's a little bit harder in practice to achieve that, but it certainly saves us a lot of time in contrast to rewriting everything from scratch each time, which is the way it used to be done in the bad old days. Another benefit of layers is by reducing the complexity of the APIs that the app developers must understand. So this is really about trying to reduce the surface area that you need to be aware of. So what the heck does that mean? Well, if you've ever taken an operating systems course that looked underneath the API, right, looked at the memory management system, looked at the networking subsystem, looked at the file system, really looked at the implementation, the device driver frameworks, really, really complicated. Tens of millions, probably in a system like Linux or Windows, hundreds of millions of lines of code to implement all that stuff. No one in their right mind wants to need to understand all of those lines of code to write apps. They want to understand a very, very abstracted view of these things. You shouldn't have to understand, say, hardware device driver interrupt handling in order to be able to write an app. So that, again, is what a good API does at the boundaries between different layers. So using the OS as an example, if you have a nice, well-defined API here, then the hundreds of millions of lines of code, or the millions of lines of code, probably tens of millions of lines of code, to implement the operating system doesn't matter. You just have to understand maybe, a couple hundred APIs as opposed to millions and millions of lines of code. So once again, it's about trying to, shield people from low-level details they don't need to know about at a given level of abstraction. That's what layers are all about. Another thing that Android gets from using layered approaches is the ability to reuse popular protocols, popular APIs, and popular programming languages that application developers were already familiar with. So, for example, Android Linux uses TCP/IP. That implementation pretty much comes off the shelf. They probably had to do little or nothing to it in order to make it work in Android. The Linux kernel, again, they tweaked a few things, but it's largely the same, at least architecturally. The C programming language, the C++ programming language, the Java platform, those are all examples of things that are reusable in the context of Android, so they didn't actually have to go out and require developers to learn a whole new language. In contrast, other APIs, other environments for mobile devices did kind of require that, right? If you were programming for the iPhone, you had to learn Objective-C back in the day, which is an abomination of a language. They've now provided Swift, which is a marked improvement over Objective-C, but it's still not really a mainstream language. If you think back to the well, I should rephrase that. It's becoming a mainstream language. If you think about the TOB index we talked about last time, you'll see Swift, I think, now has cracked the top 10. But it's by no means as popular and ubiquitous as, say, Java or C or even C++. So people had to learn very specialized things. That's one reason, by the way, why we don't teach a lot of iOS here at Vanderbilt in our courses, because to do almost anything with iOS, it requires you to get all Mac ecosystem. So you need to have an Apple computer, you have to have Apple software, you have to have all these other things, and not everybody has that. So it would greatly restrict the kinds of things we could teach. Whereas Android, you can use Linux, you can use Windows, you can use Mac, doesn't matter. It's sort of agnostic to that. Okay, so obviously a lot of these things are available in open source form. So that's the end of the discussion of layering and layered architectures in general, and then how Android is just an embodiment of all the good practices and patterns that we've learned about over many decades of building complex software systems.